Welcome to the Clock Control Unit, CKCU chapter of the HT32 MCU basic tutorial. This chapter will introduce the HT32 MCU Clock Control Unit, CKCU from the following four aspects. CKCU Introduction, Structure, Configuration, and an application example. Part 1, Clock Control Unit, CKCU Introduction. The clock signal is a periodic pulse signal generated by the circuit to provide a uniform signal to the MCU. What is the function of a clock signal? Here we take a simple logic gating circuit in the above figure as an example for illustration. The register value is theoretically equal to the output of the XOR gate. However, there is a delay in the actual gating circuit, which causes the register value to be abnormal. Therefore, connect an edge trigger between the logic gate and the register. And the edge trigger connects a square wave signal with a certain frequency. At the rising edge of the square wave, the output level of the edge trigger becomes the input level only, and remains unchanged at all other times. This solves the problem that a delay causes an abnormal value to be given to a register during the operation of the actual gating circuit. This square wave signal is a clock signal. It is generated by the MCU clock source and transmitted to the whole MCU through the clock line. In addition to the above, in macro terms, clock signals are commonly used in peripheral applications, such as serial interface baud rates, timers, I2C and SPI clock lines. Part 2, Clock Control Unit, CKCU Structure. The Clock Control Unit CKCU provides multiple frequency and clock functions. They includes high-speed external crystal oscillator HSE, high-speed internal RC oscillator HSI, low-speed external crystal oscillator LSE, low-speed internal RC oscillator LSI, phase lock loop PLL, HSE clock monitor, clock prescaler, clock multiplexer and clock gating. The clock of AHB, APB, and CPU are derived from system clock CKSYS, which can come from HSI, HSE or PLL. Watchdog timer and real-time clock RTC use either LSI or LSE as their clock source. Then, we will use the CKCU block diagram to introduce the Clock Control Unit CKCU in detail. First, the high-speed external 4 to 16 MHz crystal oscillator HSE produces a highly accurate clock source to the system clock. There are some differences between MCUs. The related hardware configuration is shown in the following figure. The crystal with specific frequency must be placed across the two HSE pins, XTAL in or XTAL out. During PCB layout, the crystal oscillator should be located as close as possible to the MCU so that the trace lengths are kept as short as possible to reduce any parasitic capacitance. If there is a high-frequency signal line, keep away from the crystal area to prevent crosstalk. Second, the high-speed internal RC oscillator HSI with a fixed frequency of 8 MHz does not require external components, thus it is affordable. The HSI frequency accuracy ranges from -2% to +2% when VDD is 3.3 volts and temperature is 25 degrees Celsius. While the accuracy ranges from -3% to +3% under constant temperature and constant voltage conditions. The HIS frequency accuracy also can be calibrated via the configuration options, but it is still less accurate than the HSE crystal oscillator. The applications, the environments, and the cost will determine the use of the oscillators. Either the high-speed external crystal oscillator or the high-speed internal RC can be used as an input clock source for PLL. Third, the low-speed external crystal oscillator LSE with 32,768 Hz frequency produces a low-power but highly accurate clock source. The associated hardware configuration is shown in the following figure. The crystal oscillator must be placed across the X32K in and X32K out. It also needs to pay attention during PCB layout. Fourth, the low-speed internal RC oscillator LSI with a frequency of about 32 kHz produces a low-power and affordable clock source and requires no external components. After the factory calibration, the frequency accuracy ranges from -10% to +10% under constant temperature and constant voltage conditions. Either the low-speed external crystal oscillator or the low-speed internal RC oscillator can be used as a clock source for the real-time clock peripheral and watchdog timer. These four clock sources and PLL output can be used to control the MCU system clock source. When the HSE clock monitoring function is enabled and the HSE is used as a system clock or PLL clock source, if the failure happens, the system clock will automatically be switched to the HSI, and the PLL circuit will also be turned off. The system clock provides clock signals to various peripherals through the AHB clock prescaler, multiplexer, and gating circuit. Finally, the clock control unit also provides clock output function. Part 3, Clock Control Unit, CKCU Configuration. Then we'll introduce three methods for the system clock configuration. Method 1, call a standard library function, write codes, and configure the system clock. Holtec provides a CKCU standard library that covers the configuration of all clock functions. Each library comes with detailed annotations. For example, the configuration function for the system clock source. The function description is included in the corresponding comment above the function. The formal parameter CLKSRC has optional configurations. Since there are many standard libraries, we will not list them all here. Please check the corresponding HT32F series CKCU.C for details. Here's an example of how to call a standard library to configure the system clock. First, reset the clock control unit. The default system clock is the high-speed internal oscillator. Second, we can enable the external high-speed crystal oscillator and wait for ready. We can also directly configure PLL without using high-speed external crystal oscillator. Third, configure PLL. First configure HSI or HSE as PLL input clock and then configure the PLL output clock according to the clock source frequency. Fourth, configure the flash wait time. There are three options: no wait, 1 clock, or 2 clocks. Fifth, configure the AHB prescaler. Finally, configure PLL as the system clock. Method 2, directly configure the system configuration file. Then, first directly configure the system file, system HT32F5 series 01.C as shown above. And enable HSE by checking the appropriate box in the option selection. Configure PLL. Configure the system clock. Method 3, use HT32 code config to configure to generate the project. Use HT32 code config to configure CKCU and download HT32 code config from the official website. Open HT32 code config and select the desired MCU part number, and then click OK. Configure CKCU and select the high-speed internal RC oscillator by default. Configure the phase lock loop. First select the input clock source. When HSE is selected as input clock source, the HSE must be enabled. When the PLL is enabled, the output clock frequency is equal to the clock source multiplied by NF2 and divided by NF1. As above, 8 MHz multiplied by 6 and divided by 1 is equal to 48 MHz. The HSI clock is used as the system clock by default. The HCLK and FCLK are derived from the AHB prescaler. The system clock can also be derived from the following clocks: PLL, HSE, LSI, LSE. If LSE is selected, LSE must be enabled. Either LSE or LSI is also used as an input clock source of watchdog timer and real-time clock. Part 4, Clock Control Unit, CKCU Application Example. Finally, we will provide an application example to summarize this tutorial. This example is one of the standard peripheral firmware library examples. It should be used with the hardware starter kit and expansion board. Depending on the system frequency, the LED flashing speed is different. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.